Welcome back, ELE 111, part 3 of the series Parallel RL or RC circuits. Taking a look at this working problem, we see up at the top we have a parallel branch up here, and I went off to the corner here and used the product over sum formula to compute the actual impedance of that parallel branch. I don't recommend you just watch videos. I recommend you run calculations. You become quicker and very sly at how you work these if you do. Okay, so once I combine those two, they drop into the situation of becoming a combined impedance. And you see how quickly this circuit goes from series parallel to chapter 5-ish. It's a series circuit now, right? So theoretically, you should be able to solve all the voltages and currents in this three-part circuit. So we're going to start by combining all the impedances here to get a ZT down here. And it's done in series, and the phasor values for the capacitor, C1, and for the RC circuit / parallel in here are shown. It's just a simple series circuit. Once you get that, we go down and we compute the total current using Ohm's law. Very straightforward. And then we reflect. And we say, hey, we've got the total current. What does that mean about C1 up at the top? That capacitor, that gets all the current. That gets IT. We could actually calculate its voltage on the next page. Now, before we go off and do that, I want you to answer me one question. It's a series parallel circuit. Doesn't matter if there's 3 parts, 4 parts, 10 parts. Somebody says, who dominates this circuit? Where do you go? You go to the impedance total, right here where the star is. And you see the angle minus 58 says, hey, we are heavy capacitive in this circuit. There'd be no way to be inductive. There's no inductor in the circuit. So we are heavy capacitive. If the answer was below 45, minus 45 degrees, then we could say it's resistive. But this circuit is not this ZT that's sitting over here circled in red. That ZT right here is the ZT of the whole circuit. Capacitive. Continuing in the analysis and dropping in, I always recommend that you drop in the new information. See how I've dropped the current in? Do you see how I've dropped the impedance in and restated and redrawn my values? Well, that will help me from going insane when I come in here and I go, hey, I'm going to solve for the 2 currents that you see in the yellow circles. Woo, let's rub that out. There we go. I want to be able to solve for these 2 currents in green running down these channels. Now that's a parallel circuit, and I want to be more creative in this attempt, and I want to use current divider to do it. And current divider is IT is equal to IT times ZT divided by the impedance you're trying to find the current through. And the first one we're going to try is to get through the resistor, the 4K at 0. So the total current is already known right here. What I want to make note of is at the bottom goes the component that you want the current. But in blue is really important. In blue, this ZT is not. What I need over here in the blue circle is a sliver of ZT that came from the parallel circuit. Remember, current divider can only be used on a parallel circuit or a sliver of a series parallel circuit where there is a parallel section. So the ZT there is a little misleading, and you will, stick yourself in the cheek if you don't start figuring this out really quick. We've grabbed the ZT from the parallel branch. That being said, we computed the current through the first resistor, which is also known as IZ1, because we gave that resistor an impedance box, just to simplify things. And hey, we just found the current. Anytime you find the current for a certain impedance or resistance, it's a great day to calculate voltage using Ohm's law, and I went ahead and did that right there. Now, ask yourself, does your work look as wide open and detailed and documented as mine? Answer: for many of you, for some of you, for one of you, could be no. Ask yourself, why? Why would I not want to be able to see what the heck I'm working on? Why would I not want to get these circuits done right? And start documenting. Okay, the next thing to compute, we've got this capacitor up here at the top, the one that's in the parallel branch circled with 1,000 circles of yellow. And again, we go into the current divider down here, and IT is easy. ZX is just, 5K at minus 90. It's this ZT again that'll get you in the rear. And once you figured out what it was up here, you use the same ZT. Not the ZT of the whole circuit, but the ZT of the parallel branch. After you compute that current, we might as well as go get the voltage of the capacitor. And notice that we didn't really need to. If you've got the voltage of the resistor, it's in parallel with that capacitor. It would have been enough. Option 1 would have been IR1 equals IC2, because they are equal. Okay? Now, a quick check of the three currents. The total current is equal to the two currents going through that parallel branch, shows that they are equal. And that's a good thing. Good luck with your homework.